Alright, just like the divergence theorem is a very important fact which will be used over and over again as we analyze series, so is this special series that I'm going to show you in a second. It's very, very important, and you better become familiar with it, not only because itself has lots of applications which we're going to see in class, some of which we're going to see in class, but also because it is the foundation that we're going to use, sort of building block that we will use as we analyze other kinds of series. And this series is the following. First of all, we're going to call it a geometric series. And the series is said to be geometric if it has the following form. So remember, it has to be a sum or formal sum intended as the limit of a sequence of partial sums of things that look like this. So it's going to be the sum from 1 to infinity of a, where a is some number, times some other number raised to the power n minus 1. Now, another standard way of representing a geometric series is by avoiding to have complicated things in the exponent. So instead of having an n minus 1 in the exponent, we want an exponent of just n. But notice that if we start with the form you have in front of you with n equal 1, the exponent of r is 0. So all we had to do is just make the series start at 0. Remember, we said the starting point of a sequence doesn't really matter that much. So a geometric series can also be written as the sum from 0 to infinity of a times r to the power n. Okay, let's write down the first few terms of this series. Well, it's going to look like this. Oh, first of all, a is a constant, remember, so I can even pull it out of the series. Okay, but now if I write that series in its first few terms, it's going to look like a plus ar plus ar squared plus ar cubed, and so on, all the way to ar to the infinity. Well, we'll never reach there, but you know what I mean. So what this means is that this is a sum of terms, each of which is obtained from the previous one by multiplying by this common ratio r. That's why we call it r, because it's a ratio, right? So we're going to keep multiplying each term by r to get the next term. Okay. One of the reasons why this series is so important is we can actually know everything about a series like this. We can find out easily if it converges or not. If it converges, we can find out easily what it converges to. And if it does not converge, then we know exactly what it does, in what way it diverges. Okay? So here are the basic facts. So we basically can know everything about this series. So the idea is that a non-geometric series is divergent. What am I saying? A non-zero. Well, if a is 0, then of course that series is 0. But if a is 0, what I'm going to say doesn't apply. Okay. So a non-zero geometric series is divergent if the absolute value of that ratio is greater than or equal to 1. Why is that true? Well, in that case, the terms of the sequence are a times r to the power n. Well, if r is greater than or equal to 0 and a is not 0, that sequence does not go to 0, right? We're assuming a is not 0, r is at least 1. Therefore, that sequence has no hope of going to 0. And therefore, by the divergence theorem, this thing is going to diverge. In what way does it diverge? Well, if r is positive, then it will diverge to positive or negative infinity according to whether a is positive or negative. On the other hand, if r is negative, then it will alternate and basically not go anywhere in particular. Now, let's see what happens in the remaining case, that is when the absolute value of r is less than 1. Well, if the absolute value of r is less than 1, the geometric series ends up being convergent. Not only that, but I can tell you what it converges to. It will converge to a over 1 minus r. Fairly simple formula too, isn't it? So as I said, this is a very simple series. We can know everything about it in a fairly simple way, and it's going to be the building block of lots of stuff we're going to do later. Now, don't believe me? Well, even the proof is simple for this kind of situation. Okay, so let me show you how the proof goes, because it's very, very simple. Now remember that the convergence or divergence of a series depends on its sequence of partial sums, and therefore the sum of the series is the limit of that sequence of partial sums. Well, let's see what the partial sums look like. Well, the kth partial sum is going to be the sum from 1 to k of a times r to the power n minus 1, which is going to be given by a plus ar squared, etc., up to a r to the power k minus 1. All right, well, what I'm going to do is I'm going to multiply left and right side of that equation by 1 minus r. Okay? And just to make things a little bit easier, I'm even factoring that a out of that sum on the right hand side. Now try expanding that product on the right hand side. You end up with 1 times 1, and then 1 times negative r, which gives me negative r. And then I do r times 1, that gives me a positive r, which cancels the negative r. And then minus r squared. And then the next one is going to be plus r squared, which cancels the minus r squared, and so on. Therefore, all the products are going to cancel except for the first and the last one. And therefore, this expression ends up being just a times 1 minus r to the power k. All right, so that allows me to get a different formula for these partial sums, as k is going to be equal to a times 1 minus r to the k over 1 minus r. And if I take the limit as k goes to infinity of these partial sums, what do I end up with? Well, remember, the absolute value of r is less than 1. So as I take bigger and bigger powers of r to the k is going to become smaller and smaller and smaller, and in the limit, in fact, it's going to go to 0. And therefore, the limit as k goes to infinity of these partial sums end up simply being a times 1 over 1 minus r, which I can write as a over 1 minus r. So once again, basic foundational series, better remember what its properties are, and we know everything about them. We know if it converges, diverges, what it converges to, or how it diverges. Pretty neat, eh?